So now we're going to generalise the generic second derivative test for a minimum and look at this following result. For a smooth function f of x, and interior point x star is a minimum of that function f, if there exists some integer n such that all the derivatives of f are 0 at x star up to some order of derivative 2n minus 1, and the 2nth derivative is bigger than 0. Okay, and we prove this using Lagrange's remainder theorem, which is a generalisation of the mean value theorem. But first, let's look at a consequence of this condition. And the consequence we want to say is that because the 2n derivative at x star is bigger than 0, by continuity of this 2nth derivative, the 2nth derivative nearby is always going to be bigger than 0. So we'll say it like this. Okay, so by continuity, since f of 2n of x star is bigger than 0, then the 2nth derivative of f at psi is also bigger than 0 for every psi near enough to x star, and we'll phrase that as for all psi in between x star and x star plus epsilon for small enough epsilon. And this is reminiscent of what we said using the mean value theorem. Right, so that's our first statement. Now let's have a look at Lagrange's remainder theorem, and it says the function f evaluated at x star plus some epsilon can be expanded in a Taylor series up to some order as follows. Taylor series based at x star, of course. Namely, it's f of x star plus epsilon f dashed of x star plus a half epsilon squared f double dashed, and so on, up to the 2nth minus 1 derivative. So that'll be epsilon to the 2n minus 1 over 2n minus 1 factorial, 2n minus 1 derivative of x star, plus the remainder term, which is going to be the 2nth term. Epsilon to the 2n over 2n factorial times the 2nth derivative of f, and it's evaluated at some psi that's in between x star and x star plus epsilon. In other words, some psi like this. Right, now let's see what happens. Firstly, all these derivatives are 0, so every one of those terms disappears. And then put the f of x star on the left, and we say f of x star plus epsilon minus f of x star is equal to the only term remaining, which is this one, 1 over 2n factorial, epsilon to the 2n, f to the 2n psi. Now 1 over 2n factorial, that's positive. Epsilon to the 2n is epsilon raised to an even power, so that's positive for non-zero epsilon. And f to the 2n of psi, that's positive. So the net result is that this right-hand side is always bigger than 0, and hence f of x star plus epsilon is always bigger than f of x star, and hence f of x star is a minimum, as we set out to prove.